Numerical schemes for SPDEs given by Istvan Gyongy, commonly known as Istvan Gyongy.
Thank you, David. So, I am still fascinated with the Richardson method, that is the extrapolation method, and I have given many talks about it. Last time in Warwick, and I would like to continue on that topic, I would like to continue that lecture, in fact, which I gave in Warwick last April, but still it needs some introduction. For those who haven't heard the lecture or lecturing me about this topic. In fact, 2 years ago, I gave at least two on acceleration methods for finite difference schemes based on joint works with Krylov. So let me recall in general, for those who haven't heard, what is Richardson method. That is a very clever idea which Richardson had about a century ago and wanted to calculate using that idea as precisely as possible the forecast of temperature. So he wanted to solve a PDE, a deterministic PDE, as precisely as possible by using finite differences, and he had the idea that in case the value which we want to calculate depends on a parameter, let's say h, as in the case of finite differences, h can be the mesh size, then we can get better approximation, or we can improve the error of the approximation, so the accuracy more precisely, if we calculate not only for h, for a fixed h, but for other values of this parameter, for example, h half and so on. And then by using a mixture of the two, the accuracy is better. So this is possible in case when the quantity UH can be expanded in terms of H as a power series. So if we can have that is the sum of some fixed numbers, uj, j from 0 to k, and h to the j over j factorial, where a plus an error term times the h k plus 1, where it is important, so like a Taylor expansion, in fact, it is important that the uj do not depend on h, and we have an estimate independent of h. So RH is bounded by some constant independently of h. In that case, it is clear that using a mixture of different value, so taking h, h half, and so on, h over 2 to the k, and calculating our approximation for these numbers, then we can find coefficients from the corresponding system of linear equations when we write down for h, h half, and so on, this expansion. Then we can eliminate the terms which are in h lower order than k plus 1. So all these terms, so we can get a much better approximation. So the question, in which cases we can achieve such an expansion, and then together with Skulov we started to show the many cases for PDEs, deterministic parabolic and elliptic PDEs, that it is indeed possible. In fact, there is a large literature about this. What we added to that in the deterministic case, that we could consider the degenerate equations, and also in the supremum norm we could get the accuracy improved. And also we could do that for stochastic PDEs, and also for time discretizations, class of time discretizations, we could do that. So the results for SPDE were for finite difference scheme had an assumption which was the non-degeneracy assumption, which is a restrictive assumption. So we could do the expansion for deterministic PDEs under even for degenerate equations we could do that, but for SPDEs we could only for non-degenerate, so under the strong parabolicity conditions. So then we understood that it is possible to do also for the degenerate case, but unfortunately the condition which I found for that, or we found for that, is very restrictive, and that is what I talked about in Warwick last April. And now a little more progress is that in fact that condition can be eliminated, so can be weakened, or we can throw out that condition. And moreover, further progress is that we can consider more general SPDEs than before. And so this is the topic of my talk now, and also a little bit about finite elements, whether it is possible, or at least an example that it is possible to have accelerated finite elements method. Right, so this is the topic. First, in fact, I summarize the older results and then formulate some new results. And in the second part, an example for finite elements, the accelerated scheme, and to show that it is possible. Some words about this. So this is joint. The first part uses joint work with James Leahy. The second part uses in fact is based entirely on joint work with Animier. And concerning the second part, I should mention that we studied the literature concerning accelerated finite element schemes for deterministic PDEs, and we found very, very little, and we couldn't use that. So anyone who knows results in the deterministic case, we would like to know about that, because this work is still in progress and we are not happy with the result we have achieved so far. And maybe we could learn then what is done in the deterministic case. So as far as we understood, very little. So the first part. So we consider that equation, that linear SPDE, and on the whole space in X, and with an initial condition. We have some results already with Skulov in bounded domain, but still at an early stage. So here L is, as usual, second-order differential operator written in non-divergence form. Alpha, beta are indices taking values in the set from 0 to D. And M is first order operator. The coefficients depend on the time, the omega, and on the space variable. And we assume the usual measurability conditions in order the equation could be well defined. Here the W's are independent standard FT Wiener martingales or scalar Wiener processes. Well, so I mentioned that the index is alpha beta, and for B we have also an index here rho running from 1 to infinity. This is correspondingly to the Wiener process, the sequence of Wiener processes here. And as always, used in literature, or I like to use, don't write the summation, and the repeated indices means summation. So here as well, so the alpha beta runs through these indices, right? F and G are random fields, so depending on T, X, omega, it takes values for fixed T, omega, X in little L2, and the initial condition is a scalar random field. We use the Sobolev-Hilbert spaces, which this norm M, the usual definition of the D to the gamma is the derivation where gamma is a multi-index, so with elements gamma 1, gamma D, and when we write gamma 1, let's say, then that means that the D1 here is applied gamma 1 times. So that's the usual notation. So right.
In X, in which little L2, what is the norm in X?
So this is for each X and omega and T it is a sequence, and as a sequence it is in little L2.
What is the condition, I mean, with respect to it?
There will be more conditions. So these are just, I'm explaining the notation. So the main assumption is the stochastic parabolicity condition. So the equation can be degenerate. So that means here we have just that the matrix written here as I and J runs through from 1 to D is a semi-definite, positive semi-definite matrix. Now the other assumptions follow. So to formulate them, we fix an integer, non-negative integer m, and this is a regularity assumption. That means that our coefficients are smooth enough. So the aij, when I write ij, that means that I consider only the main part of the second order operator. So I and j run through the numbers 1 to D, and they have to have derivatives in X up to order maximum mn2, so at least 2 derivatives should be, and should be bounded as well. The other coefficients, so the usual measurability, are differentiable up to order m, and all the functions and all these derivatives are bounded by a constant k. Now you may ask then, what does that mean here, the differentiability of B? Here I don't write already the index rho. This means the B alpha for each alpha is a function with values in little L2, and as such a function it should be differentiable with respect to X, and the magnitude is measured in the L2 norm, and that should be bounded by K. So in case of B, that is what we mean. And the initial value should be in HM, F not measurable as usual. The F is as a function of T with values of function spaces in X should be HM valued. The G rho should be HM plus 1 valued if we fix one rho, or if we just consider G, then it should be HM plus valued, but with little with little L2. So we consider HM spaces of functions with values in little L2, and in that sense, and should be predictable, and this quantity should be finite almost surely. Maybe I write down, because this quantity comes up often. So Km U naught, which is the psi m norm squared plus the integral from 0 to t f s, that is until capital T, f t in the m norm squared plus g in the m plus 1 norm squared dt. Here this means the corresponding norm in the Hilbert-Sobolev space for functions with values in L2. Right, so this should be finite almost surely. Now a remark that we want to have finite different schemes to solve this equation. So then we should have, in fact, that our data are continuous in X, because we would like to have finite difference schemes in the X variable on a grid. So the continuity of the data in X is a requirement, otherwise it is obviously not good. So we ensure that requirement by the Sobolev embedding theorem, asking that the parameter or the integer m we fixed in the assumption, the regularity assumption, is greater than the dimension, half of the dimension, because then we have a continuous modification of the data in X. So in ft and gt, and also so the free data, and also for the initial condition, and also for the coefficients. And when we assume m greater than the dimension, half of the dimension, which we from now on will assume all the time, then in fact we also assume that we consider the continuous modifications in X. Right. So the definition. This is a standard definition for the solution. So an H not valued strongly continuous adapted process U is a solution to the system, our main system, or not system, sorry, or the initial value problem 1, 2 for the SPD. If this random process is in H1 for P cross dt almost everywhere, and moreover the L2 integral in time, when here we have the H1 norm, is finite almost surely, and the main assumption, So these are obviously needed in the formulation, but technical assumptions. Almost surely for every test function phi, smooth functions with bounded support, we have this equation satisfied for all t. So this is just the usual integration by parts, using integration by parts in the definition to define the solution. I haven't written down, but this parenthesis means the L2 product. And here and also later on. Right, so this definition, so this is the definition of the solution, or let's say so-called generalized solution, but in fact we want to have a classical solution. That means when the equation is satisfied pointwise, almost surely for every t and x, and under our conditions, in fact, that will happen. Right. This remark may be important, that we assume that m is larger than half of the dimension plus 1, and from here, if we assume that, then by Sobolev embedding, we can get that the solution utx is a continuous function, or in other words, has a continuous modification in t and x. So almost surely has a continuous modification in t and x. And again, our conditions later ensure that utx, the solution, is of that kind. Right, then we want to approximate now by finite differences. And for that, we take an h, which is a number, can be negative as well, different from 0. And we consider this problem written here, 3, 4, where the LTH and MTH are finite difference operators approximating the original operators L and M. So the notation here is first of all introduce the grid, this GH. For simplicity, we consider only the straightforward grid, that is just the H. So the standard one, that here is the coordinate system, and we take the lines in the directions of the basis vectors, and between and the distance between the consecutive ones is h absolute value, and the grid is then the points of the crossing. So nicely written is just this h absolute value time the zd, where z is the number of integers. And here is the finite difference operator defined, and here for the m, the delta alpha h, delta beta h are symmetric differences in the direction alpha and beta here, when alpha is I from 1 to d. Otherwise, when alpha is 0, then it is just the identity operator. That is just a fancy notation in order to have short writing, not to write separately the first order and the second, the first order and 0 order terms, as also in the equation, if I forgot to say then, but I think I have written down. Right, here is the definition of the symmetric finite difference acting on U, finite difference operator acting on U. So when alpha is equal to the index I, that means finite difference symmetric finite difference in the direction E sub I. And when alpha is 0, then that is the unit operator. In order to solve this this equation or this system, yes, this is our finite difference scheme, but that is only in the x variable. We can notice that this is just a system, infinite system of SDEs, labeled by the points of the grid. So we use the little L2 on the grid function space. So this is our notation for it. So L2 GH is the grid, is the set of real valued functions on the grid, such that we consider the norm written here. We need to have this h to the d in order to have the harmony with the grid. Otherwise, obviously, this is finite if and only if without the h to the d. So then this is just the usual L2 when we fix h, but h will be changed. So then that should be taken into account as well. Right. The remark is that this system can be solved easily because this is a finite. This is a linear system. So if the initial value, so the psi restricted to the grid, is in L2, and also we have this assumption that this is finite almost surely, where this means Ft, the data is restricted to, free data is restricted to GH, and in that norm, if that is finite, then it's an easy result, a standard result, and that system has a unique L2 GH valued solution. Right? So we can, under very general condition, at least as in little L2, we can solve this system. Moreover, if we have that, let's say, this parameter R is greater than the dimension, half of the dimension, then by Sobolev embeddings, we have that that this is less than or that this KR is finite. Here, this R, in fact, what I want, right. So if this is finite, then from here one can get that that the previous quantity is also finite. So this is satisfied, and therefore we have an L2 solution. And again, because our M, which is the parameter at the beginning, fixed at the beginning, is greater than d half, so this condition is satisfied, so we have a solution in L2 valued solution. So what is our aim? So let us consider an L2 valued solution. This let us denote it by UTH. And our aim is then, as it is written there, that for every x on the grid and for all t, we want to have such an expansion where the uj functions are independent of h. U with 0 is the solution of the problem, of the original problem. Here I am afraid I forgot to say as well that here U0 is the number which we want to approximate. So in this case, the solution of the as the SPDE at time t and at a grid point x. And moreover, we want that this estimate be satisfied, and in that case we can use Richardson idea, we can implement Richardson idea, and so we can improve the accuracy by taking appropriate coefficients. So the assumptions for this are listed here. First, we fix an L, and we assume this assumption 1, which says that the main, this A tilde term, which arises in the parabolicity condition, so this matrix can be factorized so that there exists such a matrix sigma, that this can be written as sigma times sigma transpose, and moreover that for this fixed L it is L plus 1 times continuously differentiable in X with bounded derivatives up to L plus 1. Here I forgot the 0, so the sigma is bounded, assumed to be bounded as well. And then if we assume this condition, then we get that the aim, which I formulated on the previous slide, can be satisfied. So this is the theorem, and that is what I presented last April at the conference or workshop in Warwick. So if assumption 1 is satisfied with L greater than the dimension half, and we have the regularity assumption, you remember that means the data and the coefficients are smooth enough, and that with M, which is greater than certain fixed number here, determined by a K and this L, for some K. Moreover, assume that the expectation of this Km term is finite, then the following holds. Then the expansion 5 and the estimate 6 hold with a constant independent of H. Moreover, the coefficients in the Taylor expansion with odd in front of odd powers, so when J is odd, they vanish, and moreover, that's also might be useful sometimes. If K is odd, then instead of this, it is enough to have a little bit milder condition for the regularity condition, which where M plays a role. Well, so I'm not going to prove or explain now how to prove this. It was quite long, and still it turns out not a very good result, as you will see on the next slide. But let me say one word about this. That in fact this is easy to see that this must be satisfied, that the odd coefficients at the odd powers must vanish. Why? Because we use symmetric differences. So there, in our scheme, if we change h to minus h, then the scheme remains the same. So the UH solution is the same as the U minus H solution of the finite difference scheme. And therefore, with H and U minus H, we must have also, it is not difficult to see, the same expansion. And that, if we look at this, that the two expansions must be the same, where if the two expansions with H and minus H are the same, so it is invariant with respect to the change. On the other hand, if I write here minus H in place of H, and j is odd, then I will have the -1. So then the usual thing, the u j and the minus uj must be the same, so they vanish. So this is an easy part. The difficult part is the expansion with the estimate. Right, so I was happy with this result, though it is not really such a good result. From here, one can get the Richardson extrapolation in the standard way, so one can find these coefficients lambda j such that if we consider that mixture denoted by u tilde h, then we achieved our aim. So here we are, that the accuracy is much higher with the order, so there is a factor k appearing there, or k plus 1 appearing there instead of just 1. Okay, why this result is not very good? There are here examples, but I'm afraid I don't have enough time. So a simple example, that if we just use 2, so mixtures of 2 in dimension 2, then we get already the accuracy of order 4. You see, for just a trivial application of the result. The second example is a more concrete example with constant coefficients a and b, and with such a special initial conditions. So a toy example, and even with a b equals 2, then this condition is satisfied. The parabolicity, stochastic parabolicity condition is satisfied. This is a toy example because the solution of this equation is easily be seen, that it is easy to see that this is what is written here, and the corresponding finite difference scheme is this one. And one can solve that explicitly, and it turns out that the solution is what is written here with phi h, sine h over h. And then if now we start to calculate just a fix at a fixed value t equals 1, we take the mesh size h 0.1, and we take just one value of the driving Wiener process, let's say 1, then it turns out that up to, I don't know, 4, 10 digit, this is the real value, the true value, the true value, and for the approximations we have these values. You see that the approximation is not very good for h equals 0.005, because they agree only in the first 2 digits. But if we take this mixture, then a very good agreement until the 5th, or how many 5th digit, right? And so, sorry, I'm still bad with this. And this level of accuracy, it's good to notice, is, right, still 10, can be achieved with a mesh size 0.008, which is in fact more than 60 times smaller than the h, even than the h hat. So it is fantastically good, at least in this toy example. But nevertheless, the theorem, going back to the theorem, is not very good. And why? So that's this remark here, that the assumption 1 is rather restrictive. So that what was assumption 1? Assumption 1 says that the matrix A can be factorize as sigma sigma transpose with sufficiently smooth sigma. But one knows that even that if A is a matrix, non-negative matrix, which is C2 bounded, then one can have Lipschitz continuous factorization, so that sigma can be Lipschitz continuous. This is an old result from the 60s of Mark Freidlin. On the other hand, if A is infinitely differentiable with bounded derivative, then they may not, then still A may not have twice differentiable sigma, such that the factorization holds. And the following example I learned from my colleague Sandy Davy. This is a very nice example in dimension 1. It is written here. For x positive, the function is this, so a scalar function. When x negative or 0, then let us take just a 0. Then one can notice that this function is positive for positive x, and moreover, one can see that it is C infinity function with bounded derivative. But on the other hand, because there are only two choices for the positive part here when x is positive, to take the square root, either the positive one or for the whole x, non-negative, or the negative one. But on the other hand, if we take the derivative twice at the points 1 over 2 and pi, when n tends to infinity, this is unbounded. So it's a simple, nice example that we cannot have C2 square root of this function, no matter how nice this function is. And moreover, and then one would think that, okay, let us weaken it, that we take another condition, that is A tilde is the sum of some matrices times its transpose. So not just one, but we take several ones. And I can easily rewrite the proof of the previous theorem in the case, for the case when instead of the assumption 1 we have this assumption 1 prime, and so one would think that is okay, but it is okay in dimension 1. But as I learned from David last time, in fact, there is an example which shows that in dimension 2, still we cannot have, even if A tilde is very smooth and with bounded derivatives, still we can't have smooth enough sigma p to get this decomposition of A tilde. So that means that this is not a very useful result which I presented, though on the other hand, the result can be applied to the filtering equation, to Zakai equation, because there naturally we get this decomposition from the system. So if the system, the observation, the signal observation system, in the signal, if the sigma is there, so the diffusion coefficients are smooth enough, then we get it. But in general, we can't get, so it would be good to get rid of this assumption. And so what I would like to report that it is possible to do, and so one can formulate then better theorem from point of view of applications. That is, assume only the following assumptions. Assumption P, which is the parabolicity condition, which automatically satisfied in the previous case by assumption 1, which is the decomposition that automatically ensures this. But now we separately assume that assumption, so the stochastic parabolicity and the regularity condition with such an M, like in fact before, and also like before, we assume that the expectation of this km. Sorry, it is square here. My notation is square. Right. Then the result holds. So one can dispense with that condition. Okay, and if one do that, then one can notice that it is possible then to go somewhat further and consider the equation, a more general SPDE, which allows us to consider also Levy processes here, because we take M here, a martingale which may have jumps as well, sequence with values in little l2. Yes, if we have an integration with respect to Hilbert space valued martingales, then we can always rewrite that as little l2 as integration with respect to little l2 martingale, right? And moreover, if we have integration with respect to orthogonal random or random martingale measures, then we can also rewrite it like this. So that means that with respect to Levy processes or Levy measures, we can also, compensated Levy measure, we can rewrite it like this. Okay, so we consider a little bit more general, or essentially I would say, because now it is not a continuous martingale anymore. This NT, for simplicity, we take it as a continuous increasing FT adapted process. Correspondingly, so L and M are the same operators as before, F and G also the free terms, and here the initial condition. And together with this SPD, we consider the corresponding finite difference scheme written here, where LTH, MTH are the same operators, finite difference operators. And then we want to approximate the previous equation by the finite difference scheme, and moreover, we want to have the results on acceleration. The main assumption concerning the martingale is that it is that the measure defined by Dubmeier process, so this bracket, is dominated by the measure defined by this increasing process. In particular, it says that this M, the Dubmeier process, is continuous. So we consider only continuous, so martingales with continuous brackets, so-called quasi-left continuous martingale in the French literature, and that covers the case of Levy processes, or the basic, so Levy martingales. Right, and then we can get the corresponding result. So when let Q be a predictable process with values in the Hilbert-Schmidt matrices, I, J are running from 1 to infinity. So infinite Hilbert-Schmidt matrices with the Hilbert-Schmidt norm, and such that its square is this matrix for I, J running through 1 to infinity, almost surely for all t, and define these coefficients. So the B bar is just the B alpha, which is little L2 valued. You remember, we multiply it by Q, by this matrix. So we get again a little L2. So, right? And similarly for the G, the definition of G bar is written here. And then the theorem, so the generalization is the following, that assume the assumptions of theorem 3, but with B alpha and G replaced by these new quantities, so modified by this Q respectively. So assume all those conditions, so that means the P and R, in fact, yes, P and R, because in the P condition that appears as well. Then there exists a unique solution for U, for the previous SPDE problem, and also for the finite difference scheme, which I have written previously. And moreover, the conclusions of theorem 3 hold. So that means we have the decomposition, we have the expansion with the necessary estimate, so we can do the acceleration by implementing Richardson methods. By the way, I am aware that Richardson method is also called Romberg method, because Romberg had this extrapolation method or used this extrapolation method to calculate or to improve the accuracy of approximating integrals. But that he did in the 50s, and Richardson first work is in 1911, so I think that maybe Richardson should be mentioned here more. Okay, so now about the finite elements, and I think, do I still have? Not really. So yes, and even couldn't. Okay, then thank you very much for your attention. Sorry that I was not able, now wanted also to show the ingredients of the proof, but everyone is welcome if interested to know. So thank you again.
Thank you very much. Setting up. Next one. We could have time for a quick question because we change over. Were there any questions or comments which can have a quick answer? No. They all want long answers, won't they? Thank you very much indeed.